Hello everyone, I'm Sir Saeed. Hope you are doing well. And today I'm going to have the second lecture of the series in which we are going to discuss significant figures and dimensions. This is AS Physics, and without wasting any time, let's start. Significant figures and dimensions. Actually, the significant figures gives the quantity quantity, while the dimension gives the quality. Means in quantity we have the measurements, and in quality we have the units. So in significant figures, all the digits from 0 to 9 are significant figures. For example, if you have 4.2 kg mass, then we have the two significant figures here. Means all the digits from 1, 2, 3, 4, 5, 6, 7, 8 and 9, means all digits from 1 to 9 are always significant figures. But we have some confusion about this 0, whether the 0 is significant figure or not. Significant figure means the digits which are going to represent the measurements. So if we have the 0 in between two non-zero, then it is significant. For example, if we have 204, it means 0 is significant figure. So we have three significant figure here. 0 is significant because it is in between two non-zero digits. In second case, if the 0 is on the left side, means 0 to 4, then this 0 is not significant figure. 0, it is not significant figure. It means in this measurement we have just two significant figures, two sig figs. In third case, if the 0 is on the right, this is critical. If 0 is on the right of two non-zero digits, then we have two options like 240, and the second one is 2.40. If we have decimal in the measurement, then 0 is significant figure. But if we don't have any decimal, then 0 is not. For example, it has two sig fig and it has three significant figures. Some more examples, like if we have 0.240, then this 0 on the right side is significant figure because there is a decimal here, but this 0 is on the left side, so this is not significant figure. So in this case we have again three significant figures. Another example, if we have 2.040, then this 0 is significant figure because it is in between two non-zero, and this 0 is significant figure because this is on the right side but there is a decimal here. So we have four significant figures here. So if I just conclude the significant figures, it means all the digits from 1 to 9 are significant figures. If 0 is in between two non-zero, then it is significant figure. If the 0 is on the left, then it is always non-sig fig. But if the 0 is on the right side, then we have to see whether we have a decimal or not. If there is a decimal in the measurement, then the 0 on the right side is significant, otherwise it is not. Significant figures are actually very important. While solving problems in paper 2, the theory paper, and while doing your practical exam, you have to consider the significant figures. For example, if you have certain values and like 3.20, it has three significant figure, and if you multiply or divide or add or something like that with another, and its significant figure is 2. So your answer, if it is 3 sig fig, it is 2 sig fig, then it is preferred that your answer must be 2 sig fig, equal to the smaller one. And if we have 3.20 multiply with 3.0, then here you have 3 sig fig and 3 sig fig, and this answer must be 3 sig fig or 4 sig fig. Both are allowed here. This is some technical things. For example, and your absolute errors, in this chapter we will study some absolute error, and you have to write one decimal place. The answer is, for example, if we have one decimal place like this one, then it has 2 sig fig. But if we have some value like 32, then it is 2 sig fig again. So if you want to round off these values up to the desired significant figures, then you can round off these values according to the required significant figures. As you know that in the absolute error you have to write 1 sig fig, so you may round the values. Like for example, we may write this value as 30. So here the 0 on the right side is not sig fig, and this is again 1 sig fig, so you may round off it. Here 3.2, you may write it up to 1 sig fig, like 0.32 into 10 raised power minus 1, but it has 2 sig figs, so we may write it as 3.2 into 10 raised power minus 1. And this is all about the significant figures. Now moving towards dimensions. As I told you earlier, that the dimensions gives the qualitative nature of the physical quantities. For example, if you have length, if you have diameter, if you have width, if you have height, in all these physical quantities the unit is meter. So if all these physical quantities have same base SI units, it means they have same dimensions. So you can add, you can subtract, and you can equate the physical quantities if they have same dimensions. ठीक है, equate the physical quantities if the dimensions are same, means the units are same. And the second thing is that the numeric constants have no dimensions, means no units. Numeric constants are dimensionless. Dimensionless means no dimensions, no unit. Numeric constant means 2, 4, 5, 20, pi. All the numbers are dimensionless. So by using dimensions we have to see two important things. For dimensions we have number one, the homogeneous equations. Homogeneous equations, and number two is deriving a formula. In homogeneous equations, we check the correctness. For example, if we have a relation like s is equal to ut plus half at square, then the units are meter for this distance, for initial velocity meter per second into second, plus this is a numeric constant having no units, acceleration is meter per second square, and the time is again second square. So the meters and meters are equal. It means this is a homogeneous equation. One more example. If you have some formula like t is equal to 2 pi under root L by g, here the units of time is second. This 2 pi has no units, so for length it is meter. For acceleration due to gravity is meter per second square, and this meter is cancelled with meter and square is cancelled with the under root, so s is s, means the second is second. Again it is homogeneous equation. For deriving a formula, if you have some formula like we are going to prove this formula like again. If the time is directly proportional with the length and gravity, then first of all you have to write it like time is equal to some constant L and G, and their powers are A and B, which are unknown. So now write the units on both sides. For time the unit is second, for length it is meter, and for acceleration due to gravity meter per second square. So you know that in mathematics we have a rule that if the bases are same you can equate the powers. For example, here the base is second, the power is 1, and on this side it is second and the power is minus 2b. So you may write it as minus 2b is 1, so b is minus 1 by 2. And for m, there is no meter on the left side, so we write m by ourselves by putting a power of 0, which means 1. And on the right side, the power is a and b, and these powers are added because the values are going to multiply with each other. And again, a plus b is equal to 0. It means a is equal to minus b, then a is equal to minus 1 by 2 means 1 by 2. So substitute these values in the above equation over there. The constant is as it is, the value the power of length is a, which is 1 by 2, and the power of g is minus 1 by 2. We may write it as constant L 1 by 2, G 1 by 2. We just divide G with L and the sign is going to change, and you may write it as it is some constant under root L by G. So the formula is proved, and in the exam you have to follow the same pattern to prove the formula. Thank you very much and good luck.